Now, we've just finished spending a lot of time learning various facts about polynomials of degree n and how to locate their zeros. What I want to do now is what I'm going to call strategy and tools, a practical checklist. I'm going to give you a list so that when you're faced with a polynomial of degree n and you're looking for its zeros, that you'll have a way of attacking that question in more or less an order that makes sense. So, let's go ahead and start. Strategy and tools, a practical checklist. What I've written down here first is the standard form of a polynomial of degree n that we've seen so many times before. It has a sub n is its leading coefficient, and we're assuming that a sub n is not 0, of course, otherwise we could have started with a lower coefficient, with a lower power of x, and then all the way down to a sub 0, which is the constant term. And I've noted that all of these coefficients, from a n down to a 0, are real numbers, so this is a real polynomial. All right. First tool I'm going to write down is really a tool that you knew at the very beginning or even before this section. This is material that we've seen before. So tool 0, let me call this tool where you recognize and recall all you know, and there is quite a bit of that, all you know about, well, let's see. What will be functions of the smallest degree, degree 0? Those would be constant functions. So constant functions, and we won't worry about that one special case, the 0 function. Constant functions, except for the 0 function, all have degree 0. We know what those look like. They have graphs that are horizontal lines. Those are quite easy. And it's easy to know whether or not they have zeros. Linear functions, those are lines. We know how to find their zeros. Quadratic functions, those are of degree 2. We know how to find those zeros. We've done that in this unit. And among the various things that you want to remember their graphs, of course, and how to find their zeros. For example, with the quadratic formula for quadratic functions and so on. Okay. Well, with that out of the way as sort of a basic reminder tool, tool 0, let's go ahead and start listing the tools that we actually know something about from this unit. So I'll call this first one tool number 1. And it's the first thing you see when you look at a polynomial of degree n. You recognize that it has degree n. So the first thing you can notice based on our development is that f of x has exactly n real or complex, again, sometimes that's redundant, but that's all right, real or complex zeros, counting multiplicities. And we always count multiplicities. And if you count them, then you will always have exactly n zeros. Although, of course, like I say, some will be repeated, possibly. All right, tool 0. And then tool 1, and now tool 2. Tool 2, once you have recognized that you have degree n and you know that there are n zeros, the next thing you might want to know is how many of them are real zeros. We explored that, and we have an answer to that. F of x has, at most, n or n minus 2 or n minus 4, etc., always subtracting an even number, real zeros. And those, of course, correspond to x-intercepts. I'll go ahead and write those down. Keep that in the mind. Corresponds to x-intercepts. And as usual, this includes the counting of multiplicities. Counting multiplicities. And one other fact that we can add here it's easy to realize, and we saw this earlier, if it has these numbers of real zeros, n or n minus 2 or n minus 4, if you start out with an odd number n, and you subtract away even numbers, you will always end up with at least one real zero. So to say that here, if the degree of f is equal to n is odd, if that is an odd number, then you know that f has at least one real zero. So that's automatic. if your polynomial is of degree 3, 5, 7, 9, any odd number, it will automatically have at least one real zero. So that's good to know. That means it has at least one x-intercept. Okay, continuing on. Tool 3. Now tool 3 is a little bit of less use than the others. It is the one where we looked at the variation in order to tell how many positive and negative zeros. Once you've narrowed it down to real zeros, we can look at the type of real zeros. F of x has. And as I mentioned before, when is 0 a zero? Well, those are cases that are always easy to check, because if there is no constant term in your polynomial, then 0 is one of the zeros of that polynomial. So I don't even mention that here because that's easy to check. F of x then has, at most, and this just looks like the real zero case, at most variation plus minus 2, etc., where you always subtract 2 again, positive zeros. And it has, at most, variation with the minus sign, variation minus sign minus 2, etc., negative zeros. So if you calculate those variations, then the most that you can have in positive zeros are these numbers, one of these numbers, or negative zeros, one of these numbers. And just in case you don't remember how the variation is calculated, let me remind you. Recall that V plus, that notation I invented, now this is not particularly standard, but it'll be sufficient for what we're doing. V plus is the number of plus or minus variations, remember what we decided was the definition of a variation, in the original function, the original polynomial f of x, and V minus was the number of plus or minus variations in f evaluated at minus x with the little minus in there. So those are both easy calculations to make, and then you'll have an idea, once you've done that, of how many positive or negative zeros there might be. Now the material from tools 1 and 3 can be gathered together very often into a handy chart, so let me go ahead and put that here before I move on to tool 4. Tools 1 to 3, and here's a handy chart you can sometimes create for yourself, of possibilities, which you will narrow down using other tools. So here you have, so far at least, possible combinations of zeros. Possible combinations of zeros. And here's the way I'm going to build this. I will first write down degree, and then a plus, which will stand for the number of positive zeros, a minus, which will stand for the number of negative zeros, and I'll use I to stand for the number of complex zeros. It's just convenient notation. And then you simply set yourself up a little box like this, where these are the titles, so I'll put a double line there, and then put vertical lines through there. The combinations, the various possible combinations, will be what's listed in the various horizontal rows here. And what will these stand for? As usual, and as I said, this is stand for degree. This is for the number of positive zeros. This is for the number of negative zeros, just so you have it on the page in front of you here. And this stood for the number of complex. And what I mean in this case are complex non-real zeros. And as you note, apart from the possible 0 being a 0, these three numbers usually add to the degree. And I say usually because if you haven't factored out any powers of x from your polynomial, if you have no constant term, and you factor out powers of x, then that will lower the degree. But when you do this kind of analysis, you're usually working with a polynomial that has been reduced to one that has a constant term. So usually this will add to the degree. And you'll see in the examples I do just what I mean by that. let's go ahead and look at tool 4 to continue our list here. And this was the one that talked about bounds, where exactly all those real zeros lived. So all the real zeros of f of x lie within. And you have choice now. One of them you'll probably use most often, but it lies within either interval minus m to m, given by one of the two following numbers m. The one I labeled a back in this unit would be m would be given by 1 plus the maximum of the numbers a sub 0 over a sub n in absolute value. Remember, we make them all positive, all the way down to a sub n minus 1 over a sub n. So it's 1 plus the maximum of those numbers. And notice that this is a list of numbers. This is not anything else involved there. That's simply a list, and you just look through the list and pick the biggest number. Or your choice is to look at the other case, where m in that case is calculated as the maximum of 1, and the sum of all those same numbers is above. A sub 0 over a sub n, an absolute value added to the absolute value of a n minus 1 over a n. And so this was a sum. Now, we saw how that worked before, and we'll see how it works again in some examples coming up. These are not very hard to deal with. Remember to divide out the leading coefficient and then look at all the numbers that are left over and take their absolute values, so drop all the negative sign. Here you look at the list and pick the biggest. Here you look at the sum and compare that number with 1. So you'll see from the examples how this works. But this is the fourth tool. And let's go ahead and list the fifth tool that I've got listed here. Tool 5. This will give us a way of referring to all of these. Tool 5, you may be able to guess a root r based on whatever you see. Maybe something that you see, maybe something you guess from the graph. So it might be trial and error based on numbers or number choices or substitutions or cleverness on your part, or from the graph, where you'll also get some ideas that you can then try back in the first part as trial and error with the numbers. Then, once you've guessed a number or you've found one by some means, divide f of x by the linear term x minus r. And what do we do that for? To reduce the number of zeros by 1. So we reduce the number of zeros by 1. So if you had a polynomial of degree 10, you reduce it to a polynomial of degree 9, and with luck, that's easier. Okay, so there are tools 0 through 5, and what would one call a strategy for using these? Well, the strategy is pretty straightforward, no mysteries here. Try tools 0 to 5, more or less, and experience will help you with this, more or less in order. And that's pretty much all that there is to be said about the strategy. Now, how would you gain enough information to use these wisely? Well, you want to work problems, and we've said this before in this course many times, to gain experience. And also, while you're working through, you might want to decide at some point whether you want exact or approximate answers. So whether you want exact or approximate answers. In this case, that would be zeros we're looking for. So, depending on your situation, you will decide whether you want approximate or exact zeros, and of course, in order to get to a place where you can use these tools effectively, you should work problems to gain experience. So, we'll stop there, and then we'll come back and we'll actually apply all of this to a couple of fairly difficult looking polynomials. Now let's go ahead and look at those two, I'm just going to do two, polynomial exercises explained. where the polynomials are a little bit more difficult than you might see in practice, but if we can work them out here, you'll be able to work them out there. So here we are. Polynomial exercises explained. And the very first thing I'm going to do is give you a chance to go ahead and apply all the tools that we just looked at. And then I'll come back and show you what I did. Now here's the first question. Locate all the zeros exactly where possible, which means if you can't, go ahead and approximate them, of this polynomial, x to the fifth minus 1.8 x to the fourth minus 17.79 x cubed plus 31.672 x squared plus 37.95 x minus 8.712. Whew. That is a lot of strange looking coefficients. But you know, if we can work it here, we'll be able to do it when all the coefficients are nice, friendly integers. So, I'll leave you with that, and go ahead and try it. All right, let's analyze this polynomial. Here's the polynomial that you were just looking at, and it certainly is of degree 5, so I can write a few things down right away in my solution. I can write down that the degree of f is equal to, the degree of f is equal to 5. So it has 5, or 5 minus 2, which is 3, or 3 minus 2, which is 1, real zeros. And all of that, which I just did, was from tools 1 and 2. So I know immediately the possible numbers of real zeros, or the possible number of x-intercepts, 5, 3, or 1. Okay, now I'm going to apply tool 3. And to apply tool 3, which was looking for the number of positive and negative zeros, I need to look at what f of minus x looks like. Now let me tell you something that will make this easier. Let me bring the polynomial back here. Here's f of x. When I substitute in minus x, remember that the minus will only affect the sign of the term if it is an odd-powered term. So if I put minus x in place of x here, I'm going to get a negative x to the fifth. For x to the fourth, there'll be no change. For x cubed, there'll be a negative. X squared, no change. X a negative. And of course, nothing will change the constant term. So if I do that with that in mind, and I know you've already done it, so I will just write down what I have. I get minus x to the fifth, as I said I would get, minus 1.8 x to the fourth, plus 17.79 x cubed, and then plus 31.672 x squared, no change there, minus 37.95 x, minus 8.712. And then having this, I want to evaluate v plus, which was the number of variations in the original function f of x, and v minus, which is the number of variations in this f minus x that I have just calculated. So let's look back at the original one. There's the original f of x. Let's look for the number of variations in sign. First one is plus to minus, so there's 1. Minus to minus, nothing. Minus to plus, there's 1. Plus to plus, nothing. And plus to minus, there's another one. So I count 1, 2, 3. So v plus is 3. So that means there are 3 or 1 positive zeros because they go down by 2's. For v minus, I have the function right here. Minus to minus, no change. Minus to plus, there's 1 variational change. Plus to plus, nothing. Plus to minus, there's another one. And minus to minus, nothing. So I see 2. So that means there will be 2 variations. So that means there will be 2 or no negative zeros. Now you see why I build a chart at this point, because I've collected information on total number of zeros, number of possible real zeros, and possible number of positive and negative zeros. I also recognize there are no zeros, so I might as well mention it. Note, 0 is not a 0. So checking positive and negative is really checking all the real numbers. And let's see where that takes me. Build my little chart here. This will be possible combinations of zeros. And I first do degree, then plus, minus, and I. And build my little table here. Now, I remember from the previous page that I could have 3 or 1 positive zeros. And if I have 3 positive zeros, then I might have 2 negative zeros. Now the degree is 5, so 3 and 2 add to 5. That means there can be no complex zeros in that case. Now I might have 3 positive zeros, but I might have no negative zeros. That was another possibility. Well, the degree is 5, so that in order for this to add up, 2 plus 3 equals 5, there must be 2 complex zeros, which is good. In that case, there are only 3 possible x-intercepts. Continuing. I've checked the case where there are 3 possible positives. If you recall, there is also possibly only 1 positive. If there's 1 positive and 2 negative and the degree is 5, that's 3, there must be 2 complex again. And if there's 1 positive but no negatives and the degree is 5, then there must be 4 complex to add up. So here is the little chart completed. And notice that all the complex numbers occur in numbers that are multiples of 2 because they have to come in conjugate pairs, and that all of these add up to 5. So there are my possibilities. Now I don't know which of these various rows, there are 4 possible rows here, I don't know which one will actually be the case yet. So I want to start gathering some information. So let's go ahead and look at what tool 4 would tell us. Now tool 4 was the tool about the boundaries. So tool 4, there were 2 possible boundaries. Boundary A said, let m be equal to 1 plus the maximum of, and let me bring the polynomial back, this is the original polynomial. We were supposed to go through the original polynomial and divide by the coefficient here. Luckily that's 1. So I actually can take all of these numbers, there are 1, 2, 3, 4, 5 of them. I take their positive versions, absolute values, so I drop all the negative signs, and then I list them here in my maximization symbol. So I have 1.8, 17.79, 31.672, 37.95, and then finally the 8.712. Well, at a glance, we know which one's the maximum. That would be this one here. And adding that to 1 gives me m is equal to 38.95. So there's my first possibility as a bound. I'm going to check the other one because if it's smaller, I'm going to want to choose it. So the other one was m equals the maximum of 1 or the sum of these numbers. But I'm just going to write sum. Because you know, if I add all of these up, it's going to be bigger than 38.95. So whatever this is bigger. And so I don't want to use it. Okay? I want the bound that is the smallest so I can look in the narrowest region on the x-axis. So I'll now use this bound. And since I have a bound, let me go to a graph. And we will look on the minus 38.95 to 38.95 by minus 1 to 1 window. We choose minus 1 to 1 just arbitrarily, just so it's a narrow window around the x-axis. But this is the boundary we just calculated. And if you do that, here's the picture you get. I did this on my calculator. I got this picture. Of course, it's symmetric, so the axes sit nicely in the middle. I get this and this, which makes it look like there are 2 zeros. But 2 real zeros can't be right or can't be correct. Why is that? Well, look back here on the little chart that we created for ourselves. How many real zeros do you have here? Well, here you have 5, here you have 3, here you have 3, and here you have 1. Real zeros include positive and negative. Nowhere does 2 occur. So that means that the picture's wrong. So what I need to do is refine my picture. And this is something you'll have to do. That's why I'm going through this process. So, refine the picture. That means look at the picture and put your crosshairs somewhere a little below that number and somewhere a little above that one. And then use that as the width of the window. So my refining brings it down to minus 6 to 6 by minus 1 to 1. And if you do that, you get a much better picture that seems to give us everything we need. Here's the picture I get with that. Still symmetric, but here's what I see in my picture. I see a line coming down like that, another line like that, one that comes over here, and then the curve seems to touch right there. So I'm getting 1, 2, 3, 4 possibilities. This possibility looks like it's approximately minus 4. This one looks like it's approximately minus 1. This one looks like it is approximately 0.2. And this one here, the one that touches, looks like it is approximately 3.3. Now, I'll let you check those out on your own. But what we want to observe from this is this entire set here on the left are obviously places where the graph crosses. So these I would expect to have odd multiplicity. Remember multiplicity? If it's odd, it's going to cross the x-axis. If it's even, it touches. This one I would expect to have even multiplicity because it seems to just touch. Now, at the least multiplicities possible, if these are all multiplicity 1 and this is multiplicity 2, that adds up to 5. 1, 2, 3, 4, 5. And it would also agree with our chart because it looks like then we'd have 1, 2, 3 positive roots counting multiplicities and 1, 2 negative. And if you remember the chart we had, 3 positive, 2 negative, it looks like this is the case. So we've got all of this information coming together. The only thing that we really need to do to make sure that we've actually found roots, at least to make ourselves happy, and to check that if these are exact or not, is to substitute them in the original polynomial. So let's go ahead. Now this is something that you will not always have work out right for you. Let's see what happens here. Checks, and frankly I'm using my calculator here because of all the big numbers in the original polynomial. Remember that original now. Here's the original with all the various strange coefficients. Putting these numbers in would be tedious, so I use my calculator. And what I find out is my approximations, f of minus 4 does equal 0. F of minus 1 does equal 0. F at 3.3 does equal 0, and f of 0.2 also equals 0. So these are real zeros of f. And this one here was the one with multiplicity 2. And all the rest, of course, have multiplicity 1. Usually when you don't mention the multiplicity of a 0, you assume that it has multiplicity 1. Now, let me be honest with you. These numbers turned out nice for me because I happen to have a good graph and I got good approximations. For example, if you'd gotten 0.19 or 0.1999 for this last one, then when you put it in the function, you wouldn't get 0. So how do you know whether you have a root or not? Well, in that case, you'd have to just go by the fact that the numbers add up, that is to say the number of zeros is correct, and also the graph suggests that there's a 0 there. You may or may not be able to get it exactly. I was lucky here, but frankly you won't always be lucky. And just because you get a small number here, if you put in 0.199, you're going to get pretty close to 0. But there's no way to tell whether that's really a root or it's simply a number that gets you close to 0. So, what do you conclude from this? You use all the information that you have to get as much as you can information about the locations of the zeros. Approximations are sometimes necessary, and that's the best you can do. But we did pretty well on this. I think it's time for you to try another one. So here's the one I'll pose to you. It's a little easier. The degree is smaller. The degree is 3 this time instead of 5. Locate all the zeros exactly where possible of this one. F of x equals pi x cubed minus a horrendous looking coefficient, 5.63 pi plus 2 x squared, minus, and an even bigger one for x, plus this constant down at the bottom. Now I hope you're not scared off by these coefficients. They shouldn't scare you off. You can still get all the information that we got previously, even though these numbers are quite large. And as I said, once you look at problems where the numbers are nice, friendly integers, everything will be much easier. So now why don't you go ahead and try this, and I'll be back. All right, let's look at this polynomial. Let me remind you of what it was here. It was this one with the pi's and all the various other ugly-looking coefficients. The degree was only 3, so it is a cubic. Now, from what you know about cubics, you can automatically guess what the graph of this looks like and what the possibilities are for the zeros. Let me go ahead and sketch in down here at the bottom what the possible pictures are for cubics. You have coming up from the left, flattening out in the middle, crossing the axis at one point there, or coming up with a big loop and crossing at 3 points, or reversing that property, coming down flat, crossing once, or with the big loops and crossing 3 times. So you already know from your experience that there ought to be 1 or 3 real roots. Now I'll confirm this with all the tools, but here's a place where tool 0, that recognition tool, can help you. Okay, solution. Well, let's see. The degree of f, as I just said, is 3. So that means there must be 3 or 1, 3 minus 2, real zeros. And that, as you recall, was from tools 1 and 2. And let's go ahead now and look at what tool 3 would give us. This will determine the difference, the number of positive and negative zeros. We already have f of x. I'll go ahead and do f of minus x. Remember, the minus will only change the powers that are odd, which is a cubic and power 1 in this one. So what I end up with is minus pi x cubed minus, and I'm just going to write it out, the same thing, x squared, plus, and the same thing, x, plus 216.784. So I'm saving myself a little trouble there. I need to know the variation for f and the variation for this f of minus x. Let's go back to f. Here's f. Let's see about the variation. From positive to negative, there's 1. Negative to negative, nothing. Negative to positive, there's another one. So I have 2, it looks like. So there's 2 of those. And for the minus x case, here is negative, negative, nothing. Negative, positive, 1. Positive, positive, nothing. So I have 1. So that means from the first one, there are 2 or 0 positive zeros. I'll just write a comma there. And then the second one, so, well, if there's only 1, you can't subtract away 2 to get any lesser number. So that means there must be 1 negative 0. And that's guaranteed. There are no special cases to look at. Okay. Well, with that in mind, let's build a chart as we did before. This is possible combinations of zeros. And this one will be simpler because there are fewer options: degree, net positive, negative, and complex zeros. The first case was, well, in the case of in negative zeros, there was exactly 1, so there can only be one possibility. For positive zeros, we could have 2 or 0. The degree here is 3, so these numbers here must add up to 3. Well, 2 plus 1 do add up to 3, so there are no complex zeros in that case. 1 and 0 do not add up to 3, so there are 2 complex zeros. Complex conjugates come in pairs, so that makes sense. So that's an easy way, by the way, to check whether these numbers are correct. If any of these complex numbers is odd, then you've goofed something back here. Okay, well, we don't know which of these cases is the one that holds, whether we have 2 positive and 1 negative, or no positive and 1 negative. But maybe tool number 4 will help us get a graph that we can narrow down and actually tell which one of those is right. In tool number 4, I'm checking the boundaries now. The first boundary is 1 plus the maximum of all of those numbers. Now let's see what we have here. The numbers that we wanted to get were, remember, we had to divide by the leading coefficient here. So I have to imagine all of these numbers divided by pi, and then pick out, with the negative signs removed, the negative signs out front removed, pick out which is the biggest. Well, I think without too much trouble you can see that this is going to be the biggest of the numbers. This is 108 times pi. So that's about 325 something, minus a little bit, but that's going to outweigh either one of these. And the division by pi is uniform throughout, so this is going to be the biggest number. So 1 plus the max is going to give us, I'll just put dots there, a number which is 1 plus, let's see, 108.392 pi minus 11.26 all over pi. And that, if you calculate it with your calculator, is going to add up to about approximately 105.8. Then if I were to check b, I'd have m is equal to the maximum of 1, and then the sum of all those numbers. Well, clearly the sum in this case is going to be bigger than this number. And so this will be bigger again. And since it's bigger, I will ignore it. So I have this. Now notice that's a pretty large number. So the interval I will be looking on is quite large. And it's not necessarily the best number. These tools that you have, tool number 4, these boundaries are not always going to be very tight. I warned you about that. But at least there is a place now that you know all the real numbers live in. All the real zeros live in. So let's go ahead and look at a graph and see what I get out of that. I'm looking at minus 105.8 to 105.8 by minus 1 to 1, just as before. I've got a picture that I will get that will look something like this. It's nice symmetric axes. And I've got what look like 2 lines coming down. So I get what apparently are 2 zeros, but again, 2 is not correct. Okay, if I look back at the chart, I know that that can't be right, because that would say I'd have 2 real zeros here, I have 3 instead, or I'd have 2 here, but I only have 1 here. So I can't have just 2. So this has to be wrong. And so I have a scale that needs to be refined. So I refine the scale again. Again, I'll just pick something here and something here that are close. And I looked at my picture, and a minus 10 to 20 seems to do it. And when I look at the picture now, things are much better. I've got axis here, got this coming down here, crossing there, one crossing just the right side of the axis. And that's why I didn't see it up here, because the scale was too large. It's so close to the axis that it doesn't show up. And then one further out here, right there. If I approximate these, I have approximately minus 7.97 here. And then this one, approximately 0.63. And the last one here is approximately 13.6. Now, all of these numbers are approximations with decimals, and I can go ahead and try them in the original polynomial if I like. Chances are good I'm going to get an approximation, and you suspect that because your original polynomial has pi in it. So I'm just going to stay with these 3 numbers here. Notice I have 1 negative and 2 positives, and if I look back at my chart, I do have a case when that's true. 2 positives, 1 negative, so this first row turned out to be the right one. So that's a good thing to do when you're working these problems. Work back and forth to see that all the information agrees. And so these are the zeros of the polynomial we just examined. And I can stop there. And then we'll move on to another topic. We'll finally leave polynomials now, polynomial functions, and move on to rational functions, which after all are polynomials over polynomials.